we're dealing with how do you calculate a confidence interval. What we have to do in this is come up with an idea of where within the normal distribution do points usually fit. Okay, let's look at it this way. We've got my hand notes. Okay, if that's supposed to be the normal distribution in the middle. If we want 95%, okay, the mean is directly in the middle and this is symmetric. If we want 95%, we have to go from the mean outward a certain amount, okay? You get 95% in the middle. That allows you 2.5% to the top and 2.5% to the bottom, so that that all adds up to be 100%. Okay, if we have 2.5% to the top over here, what would you be looking up in the table? In other words, the table number would be 97.5%, because it's the table's telling you how much is to the left of that. So we would go look up 9750. And then when we want the lower number, we go look up 0250, indicating 2.5% to the left of that. Well, let's get the normal table. Let's put that up. Okay. See, it's telling us to the left. So we want to know what is the z number that gives us 97.5%. Well, we're going to have to move the table down somewhat. Sliding the table down, we're looking in the middle of the table for 9750. I see it right there. Okay? Now, what we want to know is taking that number, reading to the outside. To the left, it tells us we're at 1.9, and then you have to slide it up and look above. We're in this column. We want the 06. So what that is saying is that 9750 falls at 1.96. In other words, when we are 1.96 times the standard deviation to the right of the mean, or above the mean, we have 97.5% of the population below that. Okay, now we go look to the other table, the normal table on the left-hand side. Okay, got this right here. Now what we're going to want to go look for is 2.5% to the left. So I'm going to have to slide this down some to get it to where I can find 2.5%. Okay, and so I'm looking for 0250, and let's see, 02 is right there. Okay, everybody see that? And to the left, that's minus 1.9, and above is 6. This is the same number in the negative direction. Okay, so what does that mean? Let's go back to our original picture. Let's see if I can fit that on there. Okay. Whoops, wrong one. That was 99%. Let's put up the 95%. Okay, here we go. To get 95% in the middle, we had 2.5% above us. We looked up 0.9750. It gave us 1.96 standard deviation. That was the z value. Then we went down to the other side and looked up 0250, 2.5% to the left. So when I subtract this minus this, it gives me exactly 9500 between them. And this is plus 1.96. This is minus 1.96. And so we can summarize that by saying that the 95% confidence interval is plus or minus 1.96. Okay? And remember, this comes out of the standard table, so they're assuming the standard deviation is 1. When we put this in with the data, this is going to be 1.96 times whatever our standard deviation is. Now, what happens if we don't have 95%? That's the other picture I had up there. If we have 99%, what are they looking for? Same process. I would go look up for a 0.5%. So I would look up 0.9950. So I get 99.5% to the left. And down here, I would look up 0050. And when I subtract those, I would have exactly 99% in the middle. Well, when I go to the table and look it up, I'm between 2.57 and 2.58. And when I get it from the computer, it tells me it is exactly 2.574. So the 99% confidence interval is said to be plus or minus 2.574. Now, if I did it for 90%, how much do I have at the top and bottom? Let's just keep the same picture here and put this in. I'd have 5% up here and 5% down there. So I would look up 9500 over here and 0500 over here, and you will find that those are at plus or minus 1.645. So that's where I get the number. So on any normally distributed population, if I want a confidence interval, a 95% confidence interval, I've got to go approximately 2 standard deviation, a 1.96 if I'm calculating it accurately. If I want 99%, I go 2.574. If I want 90%, I go 1.645. Okay? And so the mean that I calculate would be in the middle. Okay? And so my confidence interval would be the mean x bar that I calculate plus or minus my z number. So if I want 95%, it would be 1.96. And this here would be the standard deviation. Okay, I would multiply those. And so I would take my mean as my best guess, and this is also called, this piece here is also called my margin of error. That's how far off I can be. Okay, and we put that together, that makes what we call a confidence interval. And we usually specify 95%, 99%, or 90%. If they don't specify, they're talking about 95%. So when they specify, they'll tell you what it is, but in a lot of cases they won't. They'll just say a confidence interval. They're talking 95% because that is your default setting. One other item in Module 13 is the concept of the difference between confidence interval for one person or confidence interval for a group of people. If we randomly select a group, they are going to have a smaller standard deviation. Now, let me give you an example. If I go back to the example I cited in earlier modules of an IQ test, it's centered at 100, has a standard deviation of 15. And so let's just take, what's the probability that if I took somebody randomly, they would score 115 or less? Well, 115 minus 100 divided by 5. I'm one standard deviation to the right. Remember, we did this before. I look up one standard deviation in the table, the normal table, and I get 8314. What does that mean? It means 83.14% of the population scores lower than that, or the probability is 0.8314. Now, if instead of having one person take the test, if I randomly selected a group of people, for argument's sake, let's say 25 people, okay? What happens to my standard deviation? Okay? The population is normally distributed, but just to get an idea of this is going to shrink the standard deviation. Why? How does this do this? If you pick people randomly, if there's an 83% chance that one person scores 115 or less, if I take 25 people, what's going to happen? What's the chances? It's going to be a lot smaller Okay, as far as that, we're going to close into 100. Why? Because for everybody that I got taking 115, I'm going to have somebody get an 85, and it's going to average out closer to. What happens is your standard normal distribution shrinks. This distribution, although we still say it's normal, actually would be a lot taller and skinnier. That's what happens with a smaller standard deviation. And what we would have, so for example, if I take a group of 25 with that same thing, what happens? My standard deviation shrinks by the square root of the size of the group. So my standard deviation would be 15 divided by the square root of 25 if the group had a size 25, or 15 divided by 5, which is 3. Now, how many standard deviations am I away? 115 minus 100 is 15. Divide that by 3. I am 5 standard deviations away. If you go back to look at your normal table for 5 standard deviations, let me just dig it out and we'll look at what happens here. Your table dies at 3.4. And you're at 99, 98. What happens when you're out that far is you are 0.99999. We say that the chances of being out that far are 0.0000, which means what? Not that it can't happen, but that it is less than 1 in 10,000. Okay? Like if you were figuring out the chances you win megabucks, you buy tickets about 1 in 4 million, statistically your chances are 0.0000 because they always round off at 4 decimal places. You would have to go out to 6 decimal places to find your chance of winning the megabucks. Okay? And so in this case, the chances that a group of 25 people chosen randomly would have an IQ below 115 or below, it would be 99.99% or better. Okay? And this comes from the fact that fact of shrinking the standard deviation. This comes from the central limit theorem. I'll talk about that later when we talk about the normal table in more detail, but it's really important when we get a group, instead of one person, what you're doing is shrinking the size of the standard deviation. This is why the size of the group you take is going to have a huge impact on any of your calculations in there, because that's the only thing you can change is the size of the sample. You can't change the standard deviation because that exists out there. But the bigger the sample size, the smaller the resulting standard deviation. Okay, thank you.